Hey everyone, welcome to The Explainer. Today we're doing something really cool. We're making the invisible visible. Have you ever actually stopped to think about what a sound really is? I mean, it feels a bit like magic when you hear your favorite song or someone calling your name from across the room, but it's actually pure, fascinating physics. So today we're going to demystify the incredible, invisible journey of a sound wave. So let's kick things off with a pretty wild fact from our research. Did you know the sun literally roars? Scientists believe it actually makes this incredibly loud, high-pitched humming noise from time to time. But here's the crazy part. No matter how close we ever got, we would never ever be able to hear it. Why is that? What is actually stopping that massive sound from reaching us?
All right, let's dive right in. Here is our roadmap for today. First, we'll cover the origin of sound, then exactly how sound travels, the speed across mediums, the incredible silence of space, and we'll wrap it all up with a quick quiz. Okay, part 1. The origin of sound. So, before we get into the complex physics happening around us every second, let's lock down the basics. Everything starts right here with this one simple definition, a vibration. To vibrate basically just means to move backwards and forwards extremely quickly. And this is the fundamental starting point of absolutely any sound wave in the universe. Whether it's a drum skin you're hitting, your own vocal cords flexing right now as you speak, or the metal string of a guitar being plucked, that rapid back-and-forth motion is the physical spark that creates sound.
But here's the thing. A vibration all by itself? Totally useless. You absolutely need our next concept, which is a medium. A medium is basically a substance, like a solid, a liquid, or a gas, that contains particles. The sound waves created by those vibrations absolutely have to travel through these particles. These two concepts are a package deal. You just cannot have a traveling sound wave without a medium to carry it.
Moving on to part 2. How sound waves travel.
Now that we've got our vibration and our medium, let's talk about the mechanics. How do these invisible waves actually move from an object all the way into your ear? Well, the crucial thing to remember is that sound waves travel by making particles physically move backwards and forwards to pass the sound along. It's really like a giant microscopic chain reaction. A vibrating object pushes forward, bumping into the air particles right in front of it. Then those particles get pushed forward and bump into the particles next to them, and on, creating this continuous wave of motion.
Since we obviously can't see microscopic air particles vibrating, we need some physical proof, right? Just look at this image. We have small paper balls bouncing around on the cone of a loudspeaker. As the cone vibrates backwards and forwards, it literally forces those little paper balls to jump. It perfectly proves exactly how the speaker is physically pushing against the surrounding air to create a sound wave. You can also see this particle compression in action with just a classic toy. A slinky spring perfectly mimics how particles compress and expand in a sound wave. If you hold one end still and push the other end back and forth, you literally watch the wave travel down the spring. The metal rings bunch up and then spread out, passing that energy right down the line. It's exactly like particles in a medium bumping into each other to pass the acoustic energy along.
All right, part 3, speed across different mediums. So we know sound moves through solids, liquids, and gases. But how do these different mediums change the actual speed of that moving wave? Check out this speed ranking. A lot of people are surprised by this, but sound actually travels fastest through solids, like a wooden desk. Then it's fast through liquids, like ocean water. And it is actually the slowest through gases, like the air around us. If you tap on a solid table and press your ear right up against the wood, the sound transfers incredibly well compared to just hearing that same tap travel through the open air.
The why behind these speed differences really just comes down to the mechanics of matter. Solids have tightly packed particles. They are squeezed in there, meaning physical vibrations transfer from one particle to the next incredibly fast. Gases, on the other hand, have loosely packed particles that are just kind of floating far apart. Because the particles in a gas have to travel further just to bump into their neighbors, the whole transfer of the sound wave is naturally a whole lot slower.
Just to give you a concrete number for how fast that slowest speed actually is, 343. The speed of sound waves traveling through the air, which again is a gas, is roughly 343 meters per second. That is incredibly fast, but just remember, if you were completely underwater or listening through a solid steel beam, that exact same wave would be hitting you so much faster.
Which brings us to part 4, the silence of space.
Okay, so we've talked a lot about how sound relies on the particles in solids, liquids, and gases. But what happens when we hit the absolute ultimate roadblock for a sound wave, a complete vacuum? Look at the direct contrast here. Over on the left, we've got a working solid medium, someone's finger tapping, and the sound is passing easily right through the table. But on the right, we've got an electric bell trapped inside a glass vacuum jar. When a special pump pulls all the air out of that jar to create a vacuum, you can still see that little hammer hitting the bell, vibrating wildly, but you wouldn't hear a single thing. It is perfectly silent.
And here's exactly why. Space is a vacuum. There are absolutely zero particles out there to vibrate. Remember our earlier definitions? Without a medium full of particles to bump into each other and pass that energy along, the sound wave simply dies at the source. The vibration is definitely happening, but there is absolutely nothing there to carry it away.
All right, our final section, test your sound knowledge.
Okay, you've got the mechanics down. Let's do a quick interactive pop quiz to lock in the key takeaways from today's explainer. Question 1. Out of these options, which can sound actually travel through? Solid, liquid, gas, or a vacuum? I'll give you a second to lock in your answer based on what we just covered.
All right, here are the correct answers. Solid, liquid, and gas. These are all valid mediums because they contain particles. A vacuum is literally the only environment where sound cannot travel, which perfectly reinforces that fundamental rule of particle physics we've been looking at.
Question 2. We see this all the time, right? Sci-fi movies constantly show these loud, booming explosions during epic spaceship battles. Based on the real science, would you actually hear them out there in space?
No way. Totally silent? Without particles to act as a medium, explosions in space make absolutely no sound at all. It really brings our narrative full circle back to the mechanics of matter. Hollywood loves adding the dramatic sound effects, but in reality, a vacuum means a total, eerie absence of sound waves. Which brings us to our final provocative thought for the day. We started off by talking about how the sun is actually humming. Well, if space wasn't a vacuum, if the universe was actually filled with a dense gas or liquid medium, what else would we be able to hear out there? Exploding stars, colliding planets, the constant deafening roar of our own sun? Our vacuum universe actually shields us from what would be an overwhelming cosmic symphony. It's a pretty amazing thing to ponder. Anyway, thank you so much for joining me on this explainer today. I really hope you walk away with a crystal clear understanding of the incredible journey of a sound wave. Catch you next time.